afternoon. For the second talk, we have Healy from the University of Wisconsin-Milwaukee, who's going to tell us about group boundaries under semidirect products with the integers. Thank you so much, Burns.
Thank you. Thanks to the organizers for making all of this happen. I'm sure it's not been an easy task to organize an online conference. So kudos to you for doing it, and thank you, and thanks for the invitation. I guess my talk title that I wrote on my slides is a little bit different, but it's really the same thing. So group boundaries and then semidirect products with the integers. I mean, every infinite cyclic extension splits, so you can kind of think of that as the same thing. So before I get into the math, I do want to mention that I really appreciated Molly's digging up of the old conference proceedings from the third geometric topology workshop. It's really cool to be at a conference with such a storied history. And it's funny, part of that history actually is what precipitated this project. So at the geometric topology workshop in 2015 down in Fort Worth at TCU is when I first met Craig. And after his talk, I asked him a question because I had been thinking about semidirect products. And I asked him a question that you know, sort of actually eventually led to one of his students, Brian Peach's PhD thesis, and then on to this project. So this paper, everything to do with this project, kind of owes a lot of its origins to the geometric topology workshop. So I think that's a neat little bit of history. So this is going to be a talk about group boundaries. It's sort of a mixed geometric topology and geometric group theory. So I'm going to try to motivate some of the geometric group theory first. So hopefully you've seen this definition before, but in case you haven't, one way of giving a boundary to a certain class of group is, or let's start with, I guess, a boundary of a space. If you have a delta hyperbolic metric space, then you can give it a boundary in the form of the Gromov boundary, which is just pick a base point, consider all geodesic rays emanating from that base point, and consider two rays equivalent if they stay bounded distance for all time. And that's one way to give a boundary to a space. And then, so how do you give a boundary to a group? You use group actions. So we're going to shortcut the adjectives proper, co-compact, and bi-isometries to geometric. And if I'm considering an action on a space without a metric, I'll use geometric just to mean proper and co-compact action. So then using the idea of group actions, you can give a boundary to a group if you're careful by giving it the boundary of a space that it acts on geometrically. And I do want to emphasize being careful, but in the case of hyperbolicity, you don't have to be careful. You just say, okay, the Gromov boundary of a group is just the boundary of any hyperbolic space that acts on geometrically. And that's an object that's well defined up to something called quasi-symmetry, which is a sort of metric equivalence, but you can just think about it as homeomorphism. So the takeaway from this slide should be that for groups which act geometrically, that is properly, co-compactly, and bi-isometries on delta hyperbolic spaces, then they have some natural way of making sense of their boundary. Okay, so what we're going to do is we want to extend this class of group that we understand the boundary for, and part of the reason for that is because not every group acts on a delta hyperbolic space nicely. So we're gonna broaden our groups by broadening our spaces. So we want to consider a very generic class of topological space if we can. So to do that, we're just going to really quickly introduce this idea of an absolute retract, which is sort of the most generic category of topological space we want to consider. So a space which is locally compact and is contractible is an absolute retract if it has this funny property, which is that if you embed that space into as a closed subset of another space, some neighborhood of that embedding retracts onto the space itself. So maybe you've seen absolute retracts before. I know some of you certainly have. But if you haven't, the picture you can sort of keep in mind, just think of CW complexes are sort of the nicest version of this, and it's not really too much far and away more generic than that. If you think of CW complex every time you see absolute retract for the rest of this talk, perfectly good approximation. Okay, but this is the generality we're sort of aiming to work in order to capture the broadest class of space that we can. All right. So I want to tell you about boundaries of spaces. So this is one property that Gromov boundary of a delta hyperbolic space has that we're going to sort of mimic. And so to do this, let's think of a copy of maybe H3, okay, and then we sort of attach, you sort of imagine attaching a copy of S1 onto it, and this sort of it compactifies the space, and it compactifies this space in such a way that you just sort of glue this to this visual boundary. This is the Gromov boundary in this case. And what property does this have? Well, you can sort of imagine.
Burns, sorry to interrupt. If you're going to go to H3, you probably want to glue H2 onto it, right?
You're absolutely right. This should be H2. My apologies. Thank you. Yeah, exactly. And so this boundary has the property that we can pull it into the space. And as soon as you start pulling into the space, you immediately come into this space. So that's what a Z-set is. A Z-set is going to be any sort of topologically trivial subset of the space where you can homotopically retract it inwards without changing the homotopy type. So for instance, a one-point compactification does not meet this criterion because you can't bring that in without changing the topological type. Okay. And if you sort of attach too much onto the space, then or you attach the interior, for example, you're not going to be able to pull it off itself. So it's sort of negligible in the sense that you can immediately move off when you homotope inwards in some kind of natural way. Okay, so again, if you think about compactifying a hyperbolic space by geodesic rays, you sort of imagine retracting along those geodesics. Okay, so this brings us to the notion of a Z structure on a group. So this was Bestvina's attempt at sort of generalizing the idea of Gromov boundaries for hyperbolic spaces back in the 90s. He sort of wanted to pull out as much as he could of that structure to use to analyze the group while not requiring this sort of stringent metric condition. So you'll see there's no metric condition anywhere in the definition. It's purely topological. We'll be able to do everything we want to essentially with metrics, but for now, Z structure, what you say is it's two spaces, really. It's a space that the group acts on properly and co-compactly, and that's X here, all right? And then it's some Z set that you attach on here with sort of these conditions. So first is that the Z set needs to compactify the space. Okay, so X bar, which is X together with Z in the way that you topologize it, it needs to be compact and it needs to be an AR. Again, AR, just think nice space. When I give this talk to an audience, it's purely geometric group theorists rather than geometric topologists. I don't even bother with ARs. I just say, think of a nice space. Think of a space that's very well behaved. The boundary has this homotopy property, negligibility property from the previous section, from the previous slide. Okay, so you can sort of pull it in. And then it's got this kind of interesting condition that is called the nullity condition. And basically all this says is that when you topologize with this boundary, you consider consider a compactum K. As you sort of translate this around, okay, it can, be large, for a little while, but eventually when you consider an open cover, all right, and that open cover has to cover the boundary as well, eventually you're going to move into these neighborhoods, and you're going to move into, in particular, some open set around the neighborhood. So if you think of your picture of H3, so H2, okay, and you think of one of those Escher drawings, and you take a pentagon, as you move off towards that boundary circle, okay, you look smaller and smaller and smaller. That's essentially what this nullity condition is trying to achieve, and it's just making sure you've glued on the correct sort of topological type of boundary. Okay, so this is just a generalization of Gromov boundaries for hyperbolic groups, but without that metric condition. But the nice thing is that we can actually recover metric tools by just saying, actually, once you've specified a Z structure, you can give that absolute retract space a metric such that that G action becomes an isometric action. Okay, so you do recover the ability to use metric tools, but you want to start with the most generic case. You just want to start with a topological space. In addition, you could ask for a fifth axiom to hold. You could ask that the action of the group on the space X also extends to a nice action on the whole compactified space, or equivalently on the compactum that you Z compactify with as well. That's going to be called an easy structure, the E for equivariant. Okay. So you don't get homeomorphic rigidity of the Z set boundary as much as you might like that. One reason you would not expect that is because that kind of rigidity doesn't happen for cat zero spaces either. Visual boundaries of spaces acted on geometrically by the same cat zero group may fail to have homeomorphic boundaries for Crook and Kleiner. So there is this kind of natural notion of equivalence, which is shape equivalence. Again, you either, if you've heard of that before, it might be something natural to you. It's not a definition I want to get into right now, but it is, you shouldn't expect these boundaries to be too very different for the same group. Okay, there is some kind of well-definedness to them. Okay. So easy structures, all Gromov boundaries for hyperbolic groups are easy structures. And if you take a group acting geometrically on a cat zero space and you give that the visual boundary with any parameter, then that turns that space into an easy structure for the group as well. So this is strictly a generalization, and we sort of know good examples already. So we have some building blocks for these group boundaries, right? Cat zero groups, hyperbolic groups. Okay, that gives us a nice base to start from, but it says, it begs the question, what else can we do? How can we enlarge this class of groups for which we can give them a boundary in some sensible way? Okay, so a student of Craig's in 2011, or at least that's the date that I think the archive thing went up that I looked up, Carrie Terrell, she said that you she showed that this class of group is closed under direct products and free products. Okay, so you can take two groups that emit Z structures and even easy structures, I believe, and you can build Z structures for the direct product and the free product just using the Z structures and the Z sets that you had for the constituent pieces. And sort of importantly to today's talk, what happens when you take the direct product is that the Z boundary you get for the direct product of those two groups, you get that the Z boundary is the join of those Z boundaries. Okay, so if you sort of have this, space X here, and then you cross it with sort of space Y, this is sort of the picture you should have in mind. Then here's sort of your boundary for X, and then here's sort of your boundary for Y, and then you'll get something that looks like the join between these as the boundary of X cross Y, or the space that you get the direct product at. Okay, so again, similar to the construction in the cat zero case. Okay, so here is the result that originally was in Brian's dissertation, and that Craig and I have been working on polishing up and doing applications for. Really, I mean, this should probably just be Brian's thing here. He did the bulk of this work for his dissertation. And what he says is that, okay, if you have a torsion-free group and that group admits a Z structure, then anytime you form a semidirect product with Z generated by some element of the automorphism group of G, then you can give that a Z structure where the Z set is equal to the suspension of Z. So the reason I highlight the direct product case is that if you take the direct product with Z, you will of course get the S0 boundary of Z, right? So the boundary of Z is just S naught. Okay, take that, and then if you have the boundary of G, every group boundary looks like a circle when I draw it. Then what you get here is you get the suspension like you might expect. But what's a little bit surprising is that in this semidirect product structure, even if this is twisted, even if P is highly non-trivial, okay, it could be infinite order or something, you're still going to get the suspension of Z being your group boundary. And the reason for that becomes a little bit more clear if I have time to talk about the proof. but it basically says that you can Z-compactify the semidirect product with Z just the same way you would if you were just taking the normal direct product with Z. Sorry. And essentially the way that works is if you take, right, you take X and now maybe you take, you've got some map, okay, Fx, so F takes X to itself, and you sort of glue this together in sort of this twisted way where you twist by F at each level. And so from down here at this level, it's another application of F. And you create this thing called the mapping telescope of X with this map F. And so F is some map that corresponds to the automorphism that you've chosen. And what you do to give this gadget a Z set is you essentially construct a really nicely behaved homotopy equivalence between it and just the nice normal regular product space X cross R. Okay, and so once you're in X cross R, you could just give it the nice Z set that it wants to have, but there's a lot of technicalities that go into you've got to build this Z compactification with these extra levels of control so that when you move back and forth, let's say we've got a homotopy equivalence between these spaces, which is what's constructed in the proof of the theorem, you need to be able to do that in such a way that that compactification still makes sense when you pull it back to the twisted mapping telescope space. Okay, I do want to talk about the applications, so I'm going to kind of move on from here real quick, but if there's time, I'll talk more about that construction. But the thing that might be interesting to know here is this torsion-free hypothesis. And part of the reason for that is a lot of the ways we can get these maps to work nicely is by using covering space theory. And of course, if you have torsion, that becomes a lot harder. So I'm putting it sort of a catty slide here, which is that you can extend these statements for groups without the torsion-free hypothesis if you're willing to introduce a few more technical hypotheses. And so here's an example of one of those statements that says, okay, if you have a group that has torsion, then what you need to do in order to mimic the prior construction is you need to make sure that there is this sort of map, okay, that you can make sense of this correspondence, okay, between the automorphism and a map of F that induces that same sort of action on the space that corresponds to the action on the group. Okay, when it's not immediately clear when that exists. Okay, if you're torsion free, then you can use covering space theory and recover it immediately. But in general, if you have torsion, you have to make that kind of assumption. So let me tell you real quick about the things that you can do with this kind of a statement. And to me, I'm most excited about this slide. So two things that you can use this to conclude is one is that all closed three-manifold groups admit Z structures. Of course, for some closed three-manifold groups, that's not surprising. Again, if you have a hyperbolic manifold, no problem. If you have a manifold whose universal cover admits a cat zero structure, also no problem. But you have things in here like nil manifolds, sol manifolds. You also have to consider non-geometric manifolds. You have mixed manifolds that you kind of have to piece together. So just sort of chasing down the different details, you can kind of worry about these case by case. I think the most interesting one is the PSL2R universal cover. That one's kind of funky. But again, using special properties about each one of these geometric cases and then putting them together using the JSJ decomposition, you can conclude Z structures for closed three manifolds. The other one that kind of is sort of analogous to the fact that this works for nilpotent groups is that we can also use this to conclude that all finitely generated nilpotent groups admit Z structures. And the reason I think that this is particularly neat is because the examples that came before, the examples that Vespina was generalizing were cat zero groups and hyperbolic groups. And nilpotent groups are neither of those things. Nilpotent groups, if they're not abelian, are not cat zero, and if they're not virtually cyclic, they're not hyperbolic either. So for larger Hirsch length nilpotent groups, you actually don't have a good notion of group boundary. But the fact that you can use this direct product structure for nilpotent groups gives you the ability to use induction and apply this main theorem sort of iteratively. And then there's a little bit of futzing you have to do with torsion. I didn't make the torsion-free hypothesis in this second statement. So there is some futzing to do with torsion, but you can do that too. I was hoping to have a little bit more time by the time I got to these slides, because the most geometric topology of all the slides it occurs here, which is to talk about the Novikov conjecture. But let me just sum up these last couple of slides by saying that in the torsion-free case, if you have an EZ structure, you satisfy the Novikov conjecture. And Rosenthal, who I actually believe is in the audience right now, which is really cool, Rosenthal has a result that talks about if you do have torsion, or if torsion is permitted, then there's sort of this extra structure you can put on these spaces that admit G actions and conclude split injectivity of the Baum-Kahn map, which is related to the Novikov conjecture. And you can sort of put those things together to get sort of these neat little corollaries that come out of this in relation to the Novikov conjecture. But maybe, I believe I'm a minute over, so maybe I'll stop there.
Well, thank you so much, Burns. Maybe we can thank our speaker again virtually. Let's see if I can. There we go. I'll give you a thumbs up. I'll give you clapping. I'll give you tears and balloons. Does anyone have any questions for Burns?
Burns, could we go back one slide?
Yes, absolutely.
Yes, this. Thank you.
Yeah, so this is the example of something you might be able to, or you can conclude using these techniques, and it's sort of, you can tell there's a lot of hypotheses here, but the reason I highlighted this particular corollary is because, again, if you do a semidirect product of a hyperbolic group, or I should be careful in what I say and not say something that's false. But I'll say it this way: if you're careful with how you apply these results, you can construct, and to my knowledge about the literature, which granted is limited, you can construct examples of groups that satisfy Novikov that weren't previously known to. And I think I got all the hypotheses on this slide. I was tinkering with it to make sure that I did, but you need to not only assume that there is a quasi-isometry of the space that realizes your automorphism, but also that quasi-isometry acts on the visual boundary, which in CAD0 land is certainly not a given.
Any other questions? If you feel more comfortable typing them in, I'm happy to repeat them for the sake of the recording.
Burns, do you think a similar technique will work for other semidirect products? Like, because you said it has the same boundary, right, as the product, because you do that.
Yeah, no, I definitely do. I very much do, and that's something that Craig and I are thinking about now. There are sort of some difficulties in the general case that aren't really present as much in this nicer case. I mean, part of that is that it's not enough just to specify an element of the automorphism group, right? When you have a general semidirect product, you know, like that, then you have this whole embedding like that to deal with, and that can do any number of things. But I'd say the sort of biggest difference is that, okay, in the case with the integers, there's no distinction between a semidirect product with Z and an infinite cyclic extension, right? Anytime you have, let me actually write this the right way. Right, this is always going to, oh man, I'm going to mess this up. But you know, that's always going to split. An extension by Z is always going to split. But in the general semidirect case, right, there's a distinction between saying semidirect products and general extensions. So that's also another place where I'd like to be able to say all general extensions, but there's a possibility that something about the split nature of the extension makes a difference. But I hope so.